Every token you watch grow on your screen is forcing your large language model to reread your entire prompt from scratch. You think it is just calculating the next word, but under the hood, the model is burning massive compute by re-evaluating text it has already processed 1,000 times. Therefore, if your output is 1,000 tokens long, that very first word gets processed roughly 1,000 times, grinding inference to a halt. But there is a hidden mechanism that changes everything, dropping this repeated work from a quadratic nightmare to a clean, linear flow, the KV cache. Today, you will master the exact 6-parameter formula that governs its size, look at why an H100 can still feel agonizingly slow, and discover why prompt caching only works from the very beginning of your input. To understand why this bottleneck occurs, we have to look at the step-by-step math of autoregressive generation. When you prompt a model, it takes the input, processes it through multiple layers of self-attention, and outputs a single new token. Therefore, to generate the next token, it must look back at the entire sequence, which now includes that new token. But because traditional attention is stateless, it has no memory of the projections it just ran. Therefore, it has to rebuild the entire computational trellis from scratch, reprojecting and re-evaluating every previous token over and over. As the sequence length n grows, the work required for a single generation step scales quadratically as O of n squared. But because this happens for every single token we generate, the total work across the entire generation pipeline explodes to O of n cubed. This is an unsustainable, compounding computational tax. What if the model could simply remember the past instead of recomputing it? Enter the KV cache. To understand how it works, we have to open up the self-attention layer, where every token embedding is split into 3 specialized vectors: query, key, and value. Think of the query, or Q, as asking, "What am I looking for?" The key, or K, responds with, "What do I offer?" And the value, or V, represents, "What do I contribute if attention actually lands here?" But here is the fundamental asymmetry that makes the cache trick work: a token's query is only ever used once, at the exact moment its own output is being computed. Therefore, after that step, the query is completely useless and can be thrown away. But the keys and values are different because they will be queried by every future token at every future decoding step. Therefore, the keys and values are providers that must be kept alive, while the query is just a temporary consumer. To exploit this, we set up a cache of slots, with 1 slot per token holding its key and value vectors at every layer. Now, when a new token arrives, we project it to its own Q, K, and V. But instead of recomputing the past, we simply append the new K and V to our growing cache. Therefore, we only have to compute similarity by dotting the new query against the cached keys, running them through softmax, and weighting the cached values. By doing this, we buy back a factor of n, dropping the per-step work from quadratic to linear. But this optimization does not come for free. We are trading time for space, and the memory cost of saving these vectors is immense. In fact, you can calculate the exact memory footprint of the KV cache using a simple 6-parameter formula. The total bytes required equal to, because we are caching both keys and values, times the number of layers, times the number of key-value heads, times the sequence length, times the head dimension, times the bytes per element. Because half-precision formats like FP16 or BF16 use 2 bytes per element, this memory accumulates incredibly fast. For example, if you run a model like Llama 370 billion in half-precision, a modest 4,000 token context window consumes about 2.5 gigabytes of memory per user. But if you scale that context to 32,000 tokens, you are looking at 20 gigabytes of cache per user, sitting on top of the massive model weights. Therefore, if you have 100 concurrent users, you need 2 terabytes of high-bandwidth memory just to hold the cache. This is why serving long context models is such a massive logistical and hardware challenge. The cache is both the solution and the price. Let's put this formula to the test with a challenge. Imagine you are deploying a model with 12 layers, for key-value heads, a head dimension of 64, running in FP16 precision. If a user sends a prompt that reaches 32,000 tokens, what is the exact size of their KV cache in megabytes? Pause the video, run the math using the formula we just covered, and drop your answer in the comments. Let's see who gets the correct number first, and then let's tackle the hardware paradox. But even with a linear KV cache, you might ask, why can large language model generation still feel slow on an enterprise-grade chip like the NVIDIA H100? The answer lies in a hardware metric called arithmetic intensity, which is defined as the number of floating-point operations, or flops, performed per byte of memory loaded. Let's look at our Llama 370 billion example. To generate a single token, the GPU has to load roughly 140 gigabytes of model weights from high-bandwidth memory, plus the KV cache, while performing about 140 billion flops of useful work. Therefore, the arithmetic intensity is roughly 1 flop per byte. But the H100 has a balance point of closer to 300 flops per byte, meaning it can process 300 operations for every single byte it reads. Because of this massive imbalance, the powerful compute cores finish their math almost instantly and sit idle, starved of data, while waiting on the memory bandwidth to feed them. Therefore, LLM decoding is not compute-bound, it is memory bandwidth-bound. To solve this, engineers use quantization to compress weights, which slashes the number of bytes we need to stream. Therefore, we can double or even quadruple the performance we extract per byte. We also use batching to share those heavy weight loading operations across multiple user requests simultaneously, making the memory retrieval process far more efficient. This memory bottleneck is also why engineers invented prompt caching. If 2 separate requests share a common prefix, like a system prompt, the system should be able to reuse the cached keys and values instead of recomputing them. But in practice, this only works if those shared blocks are completely contiguous and start from the very beginning of the prompt. You cannot cache arbitrary middle sections or suffixes. To see why, we have to look at how attention mixes information across layers. At layer 1, the key and value vectors for a token depend almost entirely on the token itself. But at layer 2, those vectors are computed from layer 1's output, which has already mixed in attention from all preceding tokens. Therefore, as information flows deeper, each token's representation becomes a product of its history. By the time you reach layer 80, the keys and values for a single token are deeply entangled with every single word that came before it. Therefore, a single change of a single byte anywhere in the prefix completely invalidates the cache from that point forward. This leads to the developer's golden rule of LLM design: always place your stable, static content like system prompts and few-shot examples at the very beginning, and keep your variable user content at the very end. Get this layout right, and you save massive prefill costs across millions of requests. Get it wrong, and you pay the full computational tax every single time. Ultimately, the KV cache is not just a clever engineering shortcut, it is the absolute protagonist of LLM inference. In fact, nearly every major modern optimization in AI, from grouped query attention to paged attention, is built to solve this exact bottleneck. They all target one of the 3 pillars of LLM optimization: we must either shrink the cache, share the cache, or extract more compute per cache load. But the KV cache is only half the battle. If you found this visual explanation valuable, hit like, subscribe, and let me know in the comments which LLM architecture deep dive you want to see next.